traded and listed company on the Australian Stock Exchange. So during these webinars, I may say, X new features coming out in the future. We have this new product, this new product. That can't be a decisive factor in you purchasing stock in the company. All right. So there's my commercial warning for you. So one quick snapshot slide of what's new in the software. We're going to go through each one of these ad nauseum today. First is the new features that are involved with all of the modules, no matter if they're spectral counting or label-free quantitation or anything in between. These include the ability to now quantify things when you have a group or replicate missing. Historically in the software, if you had a missing group, that peptide or protein was defaulted as not quantifiable. We fixed that now. It's a big addition. There's a whole host of new quantitative views which we'll go through, and some post-quant statistics in terms of visualization. So this is a volcano plot we've added to allow you to go and look at p-values relative to log2 relative expression. It's really handy. Specific to the SILAC or label-free modules, all of the peptides are now getting treated as their elemental composition representation. So no longer are the peptides being treated as just amino acids. We now know the number of carbons, nitrogens, and oxygens associated with each one of those. The good news with that is we can now calculate theoretical isotopic distributions, model those with your experimental distributions, and give you a quality score for the peak picking. This, frankly, has been most of the effort over the last several months, and it's really improved the quantification a great deal, so we're pretty excited about it. There's a whole host of new alignment algorithms for the label-free quant. These were mainly developed to support some of the larger retention time shifts we've seen, and also to account for tailing on either side of the XIC. We already mentioned the isotopic overlapping ability now between the theoretical and the experimental distribution. I will also mention you now have the ability to deconvolve overlapping precursors. This is great for things like O18, N15, label-based quantification. There's quality metrics, or what we call quant score, now associated with the peak picking, and something we always battle with is enhanced memory management. You guys continually increase the size of your projects. We continually have to update how we manage that data in the software to make sure that we scale with you. I think that's going to be an ongoing thing. Again, with all the other modules, we've added support for 2 new database search formats. We're now supporting the Protein Pilot search format. There are some specifics in the user documentation on how we support that, because it does require a conversion out of your Protein Pilot group file to an open source XML file. It's a 2-step process, pretty easy to do. Basically, the converter comes installed with your Protein Pilot software. So if you have Protein Pilot, you want to use it, you can bring it into ProteoIQ now. We're also supporting a new form of XTandem, and that is the .tandem file. That is generated when you search XTandem through the transproteomic pipeline, so you can now bring that in. Big news, also, we have a new user forum. So we have now a place for you to go, ask questions, share information with each other, and recommend new features you'd like to see. There's also a place in there for you to submit ticket requests. So if you need help on something, you can submit a private request and track their progress as you go through the support process. Okay? So let's kind of go through these new features one by one. Let's start with new features that are applicable to all modules. As I would mention, we're not going to spend much time on this today, but if you are a Protein Pilot user and you want more detailed information on how to do this conversion, just let me know. We'll send you the link to the documentation. So we've added 2 new file supports. You'll see those here. It's the proteinpilot.xml result and the xtandem.tandem. Just like you've always been able to do in ProteoIQ, you can mix search results from these file formats with any other format, and you're just going to get additional columns in your peptide view with those search-specific scores and probabilities. The changes to the missing quant group is now enabling you to quantify things that have a missing channel or a missing run. Here's an example with some iTrack data. This is an iTrack 4-plex study where we have 114, 115, and 117. 116 is supposed to be there, but it's missing. In the older versions of ProteoIQ pre-2.6, if this channel was missing, the 116 channel, that peptide would get a null quantitation value, so it would not get quantified at all. Now it's going to. The one caveat here, which I will mention, the control channel or reference group or replicate must always be present. If it is not present, you will have a divide by zero situation because we have a zero intensity value there. Thus, your peptide will not get quantified. So if you ever see peptides that are non-quantifiable, it's likely that they are missing a reference group, in this case the 114 channel. Okay. So for label-free, this means that if you have 10 groups you're wanting to compare, or 10 separate LC-MS runs, if one of those does not have that precursor XIC, not going to default the peptide to a non-quantifiable state. It will still get quantified across the other 9 runs. If you're doing a SILAC triple label experiment and one of your labels is missing, you're still going to quantify the other 2. Okay? And again, if anybody has any specific questions, just stop us and we'll address it here. A little bit more information on these missing quant values. There's a couple ways to visualize that. What I wanted to point out here is in your peptide table. Again, this is an iTrack example. In your peptide table, if you are missing a channel or a group intensity or an isotopic label precursor, that intensity will be displayed as 0, shown here, and the log-to relative expression is going to get defaulted to negative 10. Negative 10 means absent. And it's negative 10 to basically separate it in all of the plots and separate it in the table. That way you can easily sequester them out or remove them from your data set. All right? Now for isotopic quant and for label-free quant, the ability to quantify things that have missing groups or channels is automatically enabled. You're not going to have to do anything special for that. But if you are running an iTrack project, you will need to go to your Edit menu, select Reporter Quant Settings, and you're going to need to check Quantify Incompletely Labeled Peptides. The button's right here, and again, this is under your Edit menu. You just check this little box that tells the software to go ahead and quantify things that are missing channels. Click Apply, and you need to copy all your proteins or peptides to a new list. That will reinstate the changes to the quant values. And again, isotopic or label-free, you don't do anything. It's automatically accounted for. Right, now, much of the overhaul in 2.6 has been focused on isotopic labeling procedures and label-free procedures. And most of the focus for those has been on peak picking and alignment procedures. What I want to go through is the changes that are applicable to those, and they are primarily the new elemental composition mapping procedures that we have in the software, the ability to do alignment and theoretical distribution mapping, deconvolution, and we'll talk a bit about processes for reduced memory footprint here as well. This is an image of the new ability to look at theoretical isotopic distributions overlaid on your experimental mass spectra. This is actually showing a fairly complicated sample. This is O18 labeled peptides. So here we see the native O16 labeled peptide, 1 O18 label, and 2 O18 labels. And you can see each of these groups has a separate distribution overlaid. That allows us to deconvolve these and correct for underlabeling, which we'll go through in a bit. So it's a nice additional feature. All right, since we're now converting all of the peptides to their elemental composition, so carbons, nitrogens, sulfurs, oxygens, etc., there's a new page in your wizard, and this is probably the most confusing change in the software and the thing that's going to trip you up the most. But really, this is the best way we can figure out to do it for you. As you're going through the wizard setup for your project, after you've entered your search result files, mascot, sequest, what have you, ProteoIQ is going to go through and it's going to extract out all of your modifications that it sees in that search. Now for peptide amino acids, we already know the elemental composition for those, so we can go ahead and calculate that without an issue. But for modifications, that's a different story. So what we've done is we've embedded into ProteoIQ the Unimod database. And for anyone familiar with setting up a mascot search or a sequest search, typically you will go out to Unimod to find the mass of your modification that you're searching. That entire database is in ProteoIQ. So if we come across a modification that's listed with the same nomenclature as Unimod, for example here, carbaminomethyl, then we know the atomic composition for that, or the elemental composition. So we know right away that has 3 hydrogens, 2 carbons, a nitrogen, and an oxygen that we should add to your peptide. Okay? Those will be displayed here in the composition panel. So this is the view you will see in the wizard. You will see name of search. That is the name of the modification that you input into your search space. So in mascot, that is a name. In sequest or proteome discovery, that's typically a mass. You'll also see the modification name here. That is the modification name we derived from Unimod. You'll see a modification mass. That is the mass that you specified during your search. You'll also see residues. This will be populated depending on the type of search you're doing. For mascot, you typically won't see this. And then you'll see a composition. This composition is extracted from our Unimod database. Now let's say, for example, you've gone out and you've entered a modification that's not in Unimod, or maybe it has a totally different name and we can't do the mapping. You need to go out to Unimod, unimod.org, type in your mass or type in your name, locate this composition, and type it into this field. All right. Now it's critical this is accurate. If it's not accurate, then the theoretical distributions will not be accurate because we don't have the right elemental composition. Fortunately, there's some error checking that's happening in ProteoIQ where we look at the elemental composition, compare its mass to the mass you input, and we make sure those align. If they don't align, we're going to throw up an error. We're going to ask you why, and basically make you say, we're okay with that being different and move forward. All right. If you ever have a question with this, just email us. If it's not clear, we can certainly walk you through the process of setting this up. But this is probably the biggest change in terms of what you're used to in the wizard. If you ever input something wrong, there's a button you can click to update all the things you've stored in the database. Fortunately, this is a one-time deal. Once you put a modification in there, as long as you continue to search it with the same name, we will always find it for you in ProteoIQ. You're not going to worry about it. So you only have to do this when you add new things. All right, this is just an example. So when it comes up red, that means you need to put in something here. So we go out to Unimod, look it up, type it in. It's in there, turns white, click next, you're good to go. All right, the other key thing you need to know about setting up an isotopic or label-free project is we need to know some instrumentation information now. So you have to have some idea of how your precursor scans were acquired based off of your instrument parameters. We need to know resolution. ProteoIQ needs to know the parts per million mass accuracy. This is the precursor, so it's the window around the precursor monoisotopic mass for peak picking. And we also need to know if it's a centroid or profile MS1 scan or precursor scan. These are some examples of some recommended settings here. So for your high-res instruments like your FTs, your Orbitrap, your Q Exactas, anywhere between 20,000 resolution for the data we've seen works pretty well. Now there's one caveat to this with your FT and your other instruments, you can adjust that resolution for the precursor scan. So if you change that setting, say you up it to 60,000, you're going to need to update that in ProteoIQ as well. And that's a field in the wizard to do that. Also, ppm is critically important here. This is the mass tolerance for taking a peptide M over Z that we identified and picking that precursor in the precursor scan. That's the window around that precursor. The tighter that window is, the better, the less error you're going to have. Make it too tight, we're not going to find the peak. All right, so it's a delicate balance there. These are some recommended settings that work pretty well. QTOF, these have a bit more flexibility depending on what type of QTOF you use. Typically anywhere between 50 ppm to 250 ppm work pretty well depending on the vendor and how the scans are happening. And the resolution tends to be around 5,000. I will mention we're supporting lower resolution centroid quantification as well. For that, it's a very large ppm window and a smaller resolution as well. Unless, of course, you're doing some zoom scans, then you could open that up a bit. Those settings go into the MS1 quant settings, and they're also in a page in your wizard. But here, if you go to Edit MS1 quant settings, Theoretical Distributions, the MS1 quant settings control all of the, hence its name, all of the MS1 quantitation. Anything having to do with peak picking or XIC generation from your precursor scan, that happens in the MS1 quant settings, and that's under your Edit menu. Resolutions assigned here under Instrument Resolution. Here you can say we've entered 30,000. You also have the ability to update your elemental compositions for the modifications you've seen as well if you ever make a mistake. We'll come back to this. This has to do with isotopic label-based quantification. This will allow you to specify reagent impurity. So things like O18, where you can only buy 95% pure H2O18, you can account for that now in the software. Same thing with N15. All right, we'll come back to that setting. Now, the significance of resolution can't be understated here. Since we are aligning theoretical distributions shown in red and blue with experimental distributions shown in black, the resolution you set in ProteoIQ needs to be as close to the resolution of your actual experimental data. So here's an example. We have some Orbitrap data at 30,000 resolution. We get a nice tight fit, a nice tight overlay. We're going to get a good fit for that data. But if we set that to 5,000, you'll see now we're not going to get a very good overlap because we're expecting it to be much broader. So what I recommend is taking one file, running it through ProteoIQ, setting the first pass resolution, have a look at it, adjust it, look at some additional spectra, pick a good setting, because it could be that 22,300 looks the best across most of your peptides. Then you go back and run your full project after that. Right? But the key here is this fit needs to be as close as possible to the experimental data. All right, I mentioned the fit between the theoretical distribution and the experimental distribution. The reason that's so important is because one of the bigger changes in ProteoIQ now is the ability to grade or score that fit. There's also a combination of variables in there for actually grading the distribution or the selection of the taxonomic chromatograms and label-free quantification. So essentially it's a quality score. How good is the quantification? How good is the peak picking? So that you have a single variable you can select and throw out things that are bad fits. All right? So for every PSM or peptide to spectral match or MSMS event, we know the elemental composition. We can produce a theoretical isotopic distribution for that peptide. We can map that using a linear regression analysis between the theoretical and the experimental. And then we can score that. It's an R-squared. The quant score reflects the degree of this overlap, and it also has an additional feature in there for looking at the shape of your XIC. Essentially, it's the quality of the fit, the quality of the quantitation. One important thing to mention here is the quant score, you get a single value. It's a single score for every peptide. But as we know, a peptide can be identified in multiple groups. Therefore, the quant score represents the lowest of all of the scores across all of your precursor scans. It's the worst case scenario. So it could be that you have 50 precursor scans. We're going to report the worst case. That way you know which ones to throw out. And I'll show you what that means next. So here's an example of a good quant score versus a bad quant score. Again, we're here at the 30,000 resolution good fit. Here's a secondary peptide that's got a very low quant score of 0.1. We can see we're able to fit the monoisotopic peak, but we're completely missing the second two isotopes. Therefore, it's going to get penalized and almost get graded down to 0 in this case. Quant scores range from 0 to 1, 0 being the worst fit and 1 being the best fit. In practice, 0.5 is a good level to start with. There's also some additional levels to the quant score. So just to reiterate there, 0 to 1 is the standard quantification score, 1 being perfect, 0 being the worst. You also have the ability to see what we call what is defined as a negative quant score. The negative quant scores will range from 0 to -1. Okay? And the indicator for having a quant score being negative, it indicates the presence of a contaminant precursor which will have an isotope that overlaps with your monoisotopic peak of interest. If that contaminant exceeds 50% of the peak height of your monoisotopic peak, the quant score will be given a negative value. It will be considered a contaminant, and you should remove it. I'll show you how to do that in just a bit. So here we see our peptide, our precursor of interest. Here's the monoisotopic peak and the subsequent isotopes. The fit is pretty good, so it gets a fit of 0.88, but because we have this abundant precursor here that's going to overlap, it gets assigned a negative because we can't trust the peak height at that point. There's also a second set of quant scores that range from 1,000 to 1,001. This is to support our low-resolution centroid data. So if you ever see a score between 1,000 to 1,001, this means that no theoretical distribution alignment was achieved. However, we were able to align the centroid isotope peaks. So in this example, we could treat these 3 peaks as just a stick, as a centroid mass, and we're able to correlate these 3 centroid masses to each other. So the centroid masses overlap. No theoretical isotopic distribution, but it's just a simple closest to the pin mass match between your isotopes. All right, that's a fallback for your centroid analysis, or no fitting at that point. But anytime you're using an LTQ, that is what you'll see. I'll tell you what, I'm going to pause there and see if there's any questions before we move forward.
I haven't seen any questions yet, James.
Okay, great. Must be easy then. Everybody's got it. Okay, filtering by quant score. Again, all of this happens under the MS1 quant settings dialog window. If you go up to Edit, MS1 quant settings, peak detection settings, there is now a checkbox that says minimum species quant score for quantitation. If you're using a high-resolution instrument, Orbitrap, LTQFT, etc., or even a QTOF instrument, I recommend setting that to 0.5. That's a good starting point for removing things that are likely to be bad peak picking, or at least poor peak picking. Okay? What that's going to do is remove any precursors that have interference, so all of your negative quant scores. It's also going to remove anything that has an incorrect charge state and thus no overlap for your secondary isotopes. Anything that's low signal and is kind of noisy is going to typically get a bad score. And anything that's got missing isotopes, 1,000 or lower, will be removed. All right, so 0.5 is what we recommend. Visualizing the quant score, there's two ways to do that. Let me actually see if I'm showing that in the column. Good, I am. So I'll stick with this. A couple ways to visualize this now. We've added the quant score in the extracted ion chromatogram view, and there's a button to turn that off if you don't want to see it, and I'll show you where that is in a bit. So here are two precursor scans that we're using to calculate this ratio. We can see the quant score is 0.5 for these three scans, but I have one scan that's giving me a negative value. The reason these are here is because you can now click on this and go have a look at the peak and see if you want to remove it or not. So in this case, we have one of 4 total scans that's getting a bad alignment, or in this case, it's a good alignment, but it has an overlapping precursor. So again, the 0.75, the negative 0.75 is what's going to be reported in your table. You can go into your XFC, see if that's the case, decide if you want to keep it or not. Okay? And here we see evidence of that. Secondarily, they're going to be displayed in your table. And the table value is the value that will be filtered in your MS1 quant settings. So here we can see 2 columns. We see quant score and a new column called number of quantifiable species. The important thing to note here is if I did perform a min quant score filter. Let's say I told the software to remove everything below a quant score of 0.9. I just want to see really, really good alignments. The number of quantifiable species will be updated based off of the number of species that actually pass the quant score filter. So in this example, this is a SILAC data set. We have a light and a heavy species. So we have a total maximum number of quantifiable species of 2. If I go back, we have 2 possible quantifiable species, a light and a heavy. Okay? Each of them is going to get a score because they each get a fit. If one of those does not get a good fit or has a contaminant and has been removed, it will be removed from the quantitation, and my number of quant species will get updated. So here I get immediate feedback that this peptide only has one of my species that are passing that criteria. All right. For isotopic quantification, this isn't as applicable as label-free. For label-free, this is very important. Let's say you have 10 separate LC-MS runs that you're comparing to each other. That means you're going to have 10 possible quant scores that you're going to generate, 1 for each run, for each precursor. You can set that filter to, say, 0.5, and let's say you remove 5 of those. The number of quantifiable species will now be reduced to 5. So the key feature here is it's nice to have a large number of replicate runs because you can be very stringent on your quant score and still get enough species quantified to give you good statistics. So the more replicates you run, the better chance you have of getting a good fit. So you can allow things, you can be a little bit more stringent in terms of your peak picking there. The thing I want to mention here is you'll still view that XIC in the XIC viewer, but that peptide will not be, or that precursor will not be considered in your quantitative columns. All right, so you'll see a 0 there for that value. This is an example of what filtering does. This is our SILAC double label experiment. Again, a light and a heavy. The blue species in this image, so here we're plotting negative log 10 of p-value for each peptide by its log 2 relative expression, and each dot is an individual peptide. So the blue dots are all of my peptides that were quantified without any sort of quant filter. And just so you know, this data should be 1-to-1. This is a 1-to-1 mixture. All of the data should sit right square on 0 if it was a perfect world, but we know that's not always the case with mass spec data. So by default, ProteoIQ is going to quantify everything. All the blue dots are everything. You see we have a lot of things that differ very widely from 1 to 1. Those are likely erroneous peaks. If we set the quant score to 0.5 in red, you now see that most of these blue dots have been removed. We still have a couple outliers here, but most of these outliers have been removed. Okay? If we tighten that up now to 0.9, we can see that probably 90% of the outliers are now gone. We have a couple here, but these are low signal to noise and would probably be thrown out anyway. But these are, all of these have been removed at 0.9. If we get really stringent, we go to 0.99, we can see we sit now right at 0. But the bad news with 0.99 is we're throwing away a lot of good data that's real at that point. So that's too stringent. So this just shows you the effect of tightening up that fit requirement. Any questions on that? Okay. I don't see any, so I will go ahead. I'm going to escape out of this PowerPoint slide. I am going to show you in the software where those values are. So here's my peptide table. If I scroll to the right, you'll see quant score. And of course, that value is available in your peptide table options as well. It's right here in your peptide table selections. So probably when you open this up for the first time, you won't see it. You'll need to go to your column selection and turn it on. And also number of quantifiable species is here as well. Right. On the extracted ion chromatogram, jump in here. You'll now see that that's also displayed near the precursor dots, showing you which precursor scans were picked for quantitation. I'll zoom back out. You want to turn that off and hide that. If you have a large number of groups, sometimes it can get kind of jumbly. We'll likely be changing how these are organized in a later release, but right now this is what we have. If you want to turn that off, you just click Label Scans, and they'll disappear for you. Okay, so then you don't have to worry about them. I also want to point out, we'll come back to this, a new organization of the plots menus for label free and isotopic. It used to be that the raw runs were just listed directly under all species. We've now subgrouped them for easier tracking. So in this case, we have 2 groups with 2 replicates each, patient 1, replicate 1, and 2. The raw file is actually subsumed under a folder, much like you're used to seeing in Windows Explorer, for example. This gives you the ability to come in, pick 2 or more groups, and update your chart pretty easily. I also want to point out where the theoretical distributions are. Let's go out here and grab one of these. It's got a good fit, so we can have a look at it. Okay. This is your precursor scan. If we click theoretical distribution now, we will overlay that value. So there you are. It's in red. And the important thing I want to point out here for the theoretical distributions is they're not mass corrected. So when we do the R-squared linear regression overlap, the theoretical distribution and the experimental are corrected for mass shift. That way they line up perfectly. But when you display the theoretical distribution on top of the experimental, it is going to show you the native mass error associated with that precursor. So here you can see we're shifted by about, I don't know, this is about 2 to 3 ppm here. Okay. If you have a large shift, sometimes it'll be over here. So that gives you really good feedback as to the error of your actual instrument for that scan. So for the overlap, don't worry, it's corrected for, it's directly lined up, but for display purposes, we keep them separate. Let's jump back in. Now for isotopic quantification, another big feature we've added is the ability to support any isotopic labeling procedure that does not result in complete separation of your light and heavy isotope envelopes. Things like SILAC, ICAT, they typically give you enough shift to completely separate the light and heavy species. Therefore, you don't need to worry about overlap. But things like 018, 15N, some of the custom labels that are out there, they're only going to shift the mass by a few Daltons. Therefore, if you get a highly charged species, 2 to 3 charges, 4 charges, you'll get significant overlap of the precursors. And originally, ProteoIQ wouldn't deal with that very well. It would just look at the peak height and give you a ratio. But now we're able to, because we have the theoretical data, we can actually deconvolve those MS spectra, give you an accurate quantitation. That's going to happen under your MS1 quant settings, isotopic quant settings. So the goal here is to build a predicted distribution of each species, shown in red, blue, and green here. And then in this example, for this double label 018 peptide, to calculate its intensity, we would subtract the intensity of the native monoisotopic peak, subtract out the contribution for the single 018 and the 016 before we calculate the intensity. All right, it's called deconvolving. And we would do that for every single one of these species. That option is also available in your MS1 quant settings. So we go up here to Edit, MS1 quant settings, isotopic quant settings. You now have a little checkbox that says deconvolve. So you would click Apply, copy to a new protein set, and your ratio calculations will be updated. For anything that isn't necessarily 100% pure, the older versions of ProteoIQ wouldn't account for that very well either. Again, we would simply just look at the intensity and give you a ratio. However, a lot of reagents that are now being used for isotopic labeling aren't 100% pure. Typical examples of this are H2O18 and 15N. So anytime you have the labeling not going to completion, or you're starting with an impure reagent like 95% heavy water, you're not going to get a full label. Therefore, we need to account for that. So 2.6 allows you to do that, and there's two ways to set that up. The first is to add the level of purity for your isotope. That happens under theoretical distribution settings. So I mentioned this earlier, but we'll go ahead and go through it now. Here's my natural relative abundance of my isotopes. These are, it says natural, it's just what's commonly involved in nature. Unless you have a specific reason to update that, I just wouldn't. I would leave that standard. If you do have a need to specify the purity of your isotopic label, that happens under labeling relative abundance. So let's do the 018 example. We would check this box. We would tell ProteoIQ that I have purchased 95% pure H2O18 to start my labeling procedure with. Okay? The software is then going to update its theoretical distributions to fit that. And the key thing you want to look for here is once you set this purity coefficient, sorry about that, you then need to go to your isotopic quant, tell ProteoIQ to correct intensities for incomplete labeling. I'll turn that off. This is the parameter. So it's a tandem parameter. You need to correct intensities, and you need to specify the label purity.
But James, I need to interject so we don't confuse people. That's already a percent. Right? So what you have is 0.95% right now. It just should be the integer.
Oh, that's correct, Art. Thank you very much. That's why we have backup. So just type in the straight percentage here. All right, now the other thing to do once you've set this up is to actually look at the new fit of the theoretical distributions. So if we go back to my image here, let's open this up. Let's go back. If you had set this to 95, let's say you would set that to 50%, and 50% wasn't an accurate representation of what the labeling efficiency actually was. These distributions would no longer fit this experimental spectrum. So what you want to do, set your parameter, make a new protein set, pick a couple peptides to look at, and make sure that the models are fitting your experimental distribution, because it could be that what you think is the labeling efficiency isn't necessarily the labeling efficiency for the study. All right. This also gives you a good way to figure out the labeling efficiency by trial and error. You do have the option of viewing the XIC pre and post correction. So if you're going to deconvolve or you're going to correct for labeling efficiency, you now have the option in the extract chromatogram view to show the corrected intensities relative to the observed intensities, so you can see how those shift. You also see those in your table, so the intensities in the table will also change. One example of this is the ability that's always been there to look at smooth versus native intensity-based extracted ion chromatogram. So here we're looking at the native intensities. Here we're looking at a Savitsky-Goulet smoothing. Okay, before we jump into memory, any questions? Everyone's quiet today. That's good. Still working on the turkey, I think.
And I'm not seeing any questions, James.
Okay, thanks, Art. All right, so isotopic labeling and label-free quantification. Anytime you're dealing with the raw data or the instrument data, for running large projects, it can be very challenging. So we needed to come up with a solution for, or at least a temporary solution for dealing with those type of results. And this concept comes from the fact that anytime you're analyzing a natural sample, typically the most abundant proteins are going to make up most of your sampling. So for most of the data sets that we see come in-house, the most abundant, the top 50% of your proteins account for 80 to 90% of your total spectral load. So most of the computational time is spent quantifying proteins that you don't necessarily care about their ratios anyway, because they're known, they're not changing, they're well abundant. So we've added a new setting in the new Project Wizard that allows you to specify the maximum number of quantifiable peptides per protein. I recommend entering a setting of 5. If you've entered a setting of 5, this will mean that ProteoIQ is going to go through every single protein, going to rank the peptides in order of intensity, and it's going to quantify the 5 most intense peptides for each protein. This means that serum albumin will now only get quantified by 5 peptides versus 1,000 if you're doing a human serum analysis. The advantage of this approach is your low abundance proteins, where you really need that reproducibility. If a protein has only 5 peptides or less, every one of those peptides is going to get quantified. All right? So anywhere between 5 to 10 is a really good setting for this, because 5 data points is great. And it's going to be the 5 best data points because they're the most intense. All right? And I will mention that is a permanent setting that will not quantify things that are less than, that are not in the top 5 most intense species for a protein. So in your table, you will now see peptides that have 0 values for the quantitation, but you'll also see proteins that have values for the quantitation. Those are the ones that have the top 5, and I'll show you that in a bit. Okay. What does that look like? So here, if we're in the protein sequence view, again, this is double-clicking on a protein. You bring up the protein sequence view. You're now going to see peptides that have intensities, but their log-to relative expression is 0 in some cases. The important thing to point out here is if a peptide is being used for quantitation, its quantitation weight will be given a 1. All the others will be given 0s. So anytime you see a 0 here, that means it's not being used for the protein quantitation. I'll show you that as well here. See if I can find one. So let's go sort by log-to relative expression. Okay. Here we can see I have -10s, meaning they're not quantified. I can see number of quantifiable species is 0. Quant score is 1,000, a -1,000. That way it's separated. So anytime you see these negatives, these 0s, those are non-quantifiable species that weren't included, or they simply didn't pass your filter criteria. Okay. Good data will obviously have intensities associated with them. And under the Proteins tab, again, if you double-click on this, scroll to the right, you'll see this quantitation weight. 1 indicates the peptide was used to calculate the protein level quantitation. If it's 0, that peptide's not being used to calculate the protein value. Because we're now giving you the ability to filter based off of the degree of peak picking significance and the ability to remove peptides and not allow them to contribute to the protein quantitation, we needed to add a way for you to view those different peptide sets. If you remember in ProteoIQ 2.3 and earlier, there was only the option to filter by peptide score. You can look at top peptides, other peptides, redundant peptides, etc. We now have a new table option called Filter Quantitative Peptides, and this gives you 4 options. The first is to view every single peptide regardless of if it was quantified or not. All right, that's the full list. The second is to show unique quantitative peptides, and we'll get to that in the next slide, what a unique quantitative peptide means. The next is to look at peptides that were actually used to produce a protein quantitative value. So you could have peptides that were quantified that are not allowed to contribute to the protein level quantitation. So if you've done weighting, if you've done quality score filters, then those peptides sometimes will not be allowed to go to the protein level value. That is the filter you will use to see those. And that's going to be a redundant list. If you want to see a non-redundant list of peptides you use for protein quant, you need to select that option here. So let's talk a bit about peptide organization in the tables. We commonly get questions about this, so I did want to address it today for those of you that are here. Let's jump back and let's look at an extracted ion chromatogram first. Let's just randomly pick one here. See if you're any good. Okay, let's turn on all species. All right, so I'm going to have to find a good example here. Okay, here's a good example. So if you look at this extracted ion chromatogram, and let's just pick one. That way we don't need to look at several. If you look at this extracted ion chromatogram, the two dots, or the squares, or depending on the number of samples you have, sometimes you'll see triangles there as well. Those two dots indicate that MSMS was triggered at these two time points for this peptide of interest, and it resulted in a significant peptide identification. All right, so here we have one peptide. We'll move this over. Shift it over here, sorry. This peptide, this amino acid sequence, was generated by these two MSMS events. Now, the important thing to notice here is there's only one extracted ion chromatogram. So for any extracted ion chromatogram, you can have many, many MSMS events. And the result of that is a table view that will have all the list of each peptide ID by MSMS event. So every time you have an MSMS event that goes on to identify a peptide, you're going to have a peptide displayed there. So these represent, each row represents an individual MSMS spectra that resulted in an identification that passed your filters. Now, for any MSMS event, that can relate to a distinct extracted ion chromatogram. So let's look at an example. Here we have two MSMS events, both matching the same peptide with the same charge state, and exactly the same observed precursor mass, which isn't always the case. One is labeled as top quant peptide, one is labeled as other. This is based off of score. So the highest scoring species is going to be assigned as top quant peptide. The lowest scoring species is going to be designated as other. You'll note here they both get the same quant peptide ID. So if a peptide has a quant peptide ID, that means it has an extracted ion chromatogram. So this peptide relates to extracted ion chromatogram number 296. You'll also see that it has the same exact intensity for the light, same exact intensity for the heavy, and thus the same quantitative value. Two peptide IDs go into one XIC. Anytime we see a separate charge state for that peptide, or a peptide plus a new modification, that will result in a new extracted ion chromatogram, thus a new quant peptide ID and a different intensity. So you can have the same three peptide IDs, two different charge states, two different extracted ion chromatograms. Okay? So filtering by top will reduce those. So if I pick view unique quantitative peptides, this is I will get basically a list of two peptides. I will get these two tops, and I will hide the other. Those are my unique quantitative peptides. I'll pause there. Does that make sense? See if you have any questions.
I'm not seeing any questions still.
Okay. All right, let's shift gears and talk a bit about best practices with 2.6 and how we recommend going through the project setup. And you'll certainly see more of these webinars in the future, but I think now this is the process that we're recommending to all of you. The first step is if you're doing a complex sample, say more than 10 runs, we recommend reducing the number of quantifiable species down to 5. So it's going to dramatically speed up the processing. It's going to significantly reduce the final size of your project and overall make it easier to interpret. All right, so let's set that minimum number of, or maximum number of quantifiable peptides to 5 per protein. After the project's created, you then need to specify some level of statistical validation. This will ensure that you don't quantify on junk. Unless you're really wanting to dig deep into your proteome and find things that are up or down regulated that you don't have a good ID for, I recommend going ahead and just filtering by 1% FDR, 0.9 protein group probability. Again, this is contingent upon having enough data to fill those distributions and make them accurate, but that's for another webinar. We're now recommending that instead of using top 2 peak picking, that you use total area and you allow ProteoIQ to determine the area of that peak using only the top 50% of the peak. That way you don't have to deal with baseline detection or peak tailing. So the top 50% of the peak is only going to be used to calculate the area. Right? That also gives you some additional data points to help smooth it out. And since I have mentioned smoothing, we recommend now doing the smoothing algorithm and quantifying using those values, because data-dependent acquisition naturally produces jagged XICs. The smoothing is going to help clean that up a bit. And we have seen improvements on our test data sets with that. And then finally, I recommend using a minimum quant score filter of 0.5 to remove things that have bad peak fitting. So let me show you how to set all those up. If you're in your edit menu, MS1 quant settings, you're going to first go to peak detection options. We're going to select quantify using total area. And we're going to allow that area to be calculated at the top 50% of my peak. So we're not going to use the bottom of the peak, we're just going to use the top. We then recommend using the smoothing and setting a min quant score for quantitation to 0.5. Right, so those are the settings. You would click apply, select all, right click, and copy to a new protein set. That's going to instantiate those changes and will update all your quantitative values. So here's an example of that data set. What I then recommend doing is going to your number of quantified species column and selecting the peptides that pass your filter criteria. So in this case, in this data set, since we have 4 separate LC-MS runs, if you remember, let's go into here. If you remember, there's a total of 4 separate experiments. So we have a maximum of 4 possible quantifiable species. All right? Because I've applied my filter, it is possible for me to have excluded some of these extracted ion chromatograms. So in this case, for this peptide, we've deleted 2 of them. So now I only have 2 data points to compare versus 4. So I need to make a decision, how many quantifiable species do I want to include? So if you have a large project, say 20, 30 runs, you're likely going to want to bring over peptides that have passed at least 50% of those runs. All right, that way you can feel confident in the number of replicates you're going to have or the number of measurements you're going to have. Let me sort by quantifiable species here to show you how that's displayed. Let's go down here and find one. Most of these passed in this example. All right, so here's a good example for 3. Let's right-click and have a look at this. Let's view all. Let's find a better one than that. Let's find a good one to look at. Okay, here's a good one. All right, so we have 3 quantitative species that have passed my 0.5 filter criteria. So we know all of those are pretty good. We can actually go in here and look at these now. Zoom out. So now we're seeing total area. You see all of these have passed 0.5, 0.5, 0.5, and it's very busy up here. That's why I like to turn it off. But one of them was given 0. So there's really not a very good fit here. So it was removed. If I want to view only the XICs that actually passed my filter criteria, and thus I don't spend time looking at things that were junk in the first place and just confusing myself, I recommend checking this option, Show Only Quant Peptides. Click View Chart. Now you see that very bottom one that was kind of noisy went away. So let's turn that back on. This little pink guy at the very bottom, if I check it, it's now gone. So what we've done is we've cleaned up our view. That way, every time I go to view this data, I'm only going to look at the peptides that were actually quantified, or the XICs that were actually quantified. It's all the same peptide in this case. All right? So once you've applied your filter, go in, view only quant peptides and just look at those. Okay. Now, in the older versions of ProteoIQ, you would have probably manually gone through some of the proteins, looked at things that were up or down regulated, and made a judgment call. We've ordered to simplify that for you. Because we have the theoretical distribution alignment, it's robust, and because we have an onboard p-value via an ANOVA, you can move directly onto protein quantification. Originally, this was a two-step process, or it could be a multiple-step process if you have a lot of groups. The first would be to look at statistically significant quantitative values using the p-value and copying those proteins out to a new list. Then you would go and look at things that were over your fold change to find things that were not only accurately quantified, but that had a big fold change, to find things that were changing the way you'd want them to change. That's a one-step process now, so we've added a volcano plot for you. Okay, and the volcano plot is a negative log 10 transformation of your ANOVA p-value. So just to reiterate, most of you know this, the p-value is a measurement of the reproducibility and the quality of the quantitative value. So it asks the question, could this quantitative value that I'm measuring for my protein be produced randomly? What you're looking for is a p-value less than 0.05. That would indicate that it's not a random measurement, that it's actually accurate. But the trick is to combine that p-value with the fold change, or with the log2 relative expression. The volcano plot does that. So what you're looking for is each of these dots is an individual protein, and just like all the other plots, you can pick your groups or your light species or your heavy species to view. You pick which ones you want to view, and you also pick which ones you want as your reference, just like the old cluster dot plot was. We're now plotting the negative log 10 of the p-value on the y-axis and log2 relative expression on the x-axis. What you're searching for is peptides, or proteins in this case, that fall in the left quadrant and the right top quadrant as well. Anything that has a p-value, or negative log 10 p-value greater than 1.3 will have a p-value of 0.05 or less. So just to be safe, go to 1.5 and look up, and then decide where you want to draw your fold change and look left and select those proteins. Let me show you an example of that. Close this out. Let's go now to our p-value plot. That's happening under quantitative or comparative proteomics. There we are. I will mention we give you the ability to shade that by the number of peptides. So if you want to look at things that have 2 or more peptides, you just put 2 there. Let's maximize this. There we go. Sorry about that. Let me jump back in. Okay. So now what we're looking at is each dot is a protein in patient 1 and patient 2. We're looking for things that are over 1.5. So this is my level. We'll just be greedy and say 2. Okay. And then we're going to look for things that have a big fold change. So typically what you're looking for is things less than -1 or greater than -1. That's going to be a 2-fold change. So for us, let me zoom in here. For our analysis, this protein looks pretty interesting. Got a fold change of almost 3-fold and a really good p-value. And we might pick this one as well.
Interrupt you for just a minute.
Sure.
Shinji had a question. Our lab wants to use formaldehyde labeling and N-dimethylation to quantify peptides. Can ProteoIQ do that?
Yes, we've done lots of dimethylation experiments. So I'll tell you what, I can show you how to set that up right after this, if that's okay. What I'll do is I'll jump in and we'll do a quick project setup for a dimethyl experiment. Sound good, Art?
Okay.
Yeah, so the way the isotopic labeling works is you specify the mass shift of your reagent. So it doesn't matter what it is, as long as you know the mass, you're good to go. All right, so we've picked 2 proteins. What I want to point out here is you do have the ability to click and select proteins of interest. So what I'll do is I'll scroll up here. Let's go to my protein table, uncheck everything. Let's do this again. All right, so if this is interesting, I'm going to pick it. You'll see it's highlighted. Let's go ahead and pick this one and these guys. I will also mention, if you want to do it just like the other ones, you can draw a square, right-click, and select everything. All right, so now you've picked every one of these proteins. You know they have a good ANOVA, they're reproducible, and they've got a big fold change. So that's what you want. Those are the proteins you want. You can then right-click, copy those out to a new list, which is what I've done here. And we now have a list of what I call significant proteins. For those of you that don't remember, these protein sets are automatically named protein set 1, 2, 3, etc. If you ever want to rename these, you do it over here. You just put rename, type in a new name, hit go after you've checked this box, and it'll update the name. That way you can keep track of what you're doing. But suffice it to say, these are my upregulated proteins, or downregulated proteins in this case. Once you've selected those, I do recommend going through them, having a look at some of the peptides. At the end of the day, we're all mass spectrometrists. We want to take a look at the data. Double-click on the protein. This is the last new feature we've added for 2.6. You now have the option of navigating within a protein sequence view the extracted ion chromatogram. So if I right-click, pick my XIC, I now have the option, I'll move this over. This one looks great. We see good reproducibility here, big change. You now can move back and forth within the protein sequence view. So click Next. We've now stepped down to this next peptide. So it's really, really quick just to navigate through these and kind of sign off and say, this protein looks great. I'm really happy with this. So if I was going to sign off on this peptide, I'd check it and keep it for later. All right? And I would go through that process for all my upregulated proteins. I just like to look at them. And you probably do too as well. All right, last but not least is the user forum. We've had a lot of requests for this. We finally got it done. I'm pretty happy with it. Zendesk is a great company to work with. It's a good user forum. Essentially, everyone's going to get an email for this. You should have had it in your webinar invite, and we'll do another release of this as well next week, another email to you. This is a place for you to exchange ideas. So we've already pre-populated this with a number of frequently asked questions, common questions and answers. And just like any forum, this allows you to go in and ask a question. Other users of ProteoIQ can comment. We can comment, basically build a knowledge base of the software there. We've had a couple requests for new features. This is a good way for you to make them public. People can score them. If there's something you really want to see, put it in the feature request, and other people can say, that's a great idea, or that's not a great idea, and they'll grade it for you. It's like Facebook. We'll be populating this with little tips as we kind of come across helpful features. We'll add those as well, and then any announcements we have will go in here. The key thing for you is most of you, if you have a question or an issue with the software, you've been going through our website for technical support. Now, if you register with our customer community, you can submit a request here, and then your tickets or your request will be tracked. So you can always log in and see if somebody's responded to you, or if it's a sophisticated case where we're exchanging data and trying to do some debugging, then you can track the progress here in your existing request panel. So it's a good place to be. Okay. So with that, I'll open that up to any questions, and then I will also jump in and look at some dimethylation setup as well if nobody has any other questions first.
Okay, James, I have a question. I have ProteoIQ version 2.3.02 in a maintenance contract. Can I download 2.6 for free? Also, could you send me the file with the slides presented today? That's Eduardo.
Yep, everyone's going to get an email with the slides today. And if you have an active maintenance contract, you absolutely can go log into your account, download it. Any other questions there? Okay, well, I'll tell you what, if anybody, I'll give some other people some time to get some questions. I'm going to go ahead and we'll just go through a quick dimethylation project setup since everybody's here. All right, navigation panel, new project wizard. Dimethylation is going to happen under isotopic labeling. I'm going to zip through most of these screens and show you the key screen for setting up a dimethyl project. Okay. The key thing here is to specify the number of groups. So if it's a double label experiment, that's going to come later. This happens to do with the number of replicate experiments you're doing. We won't talk about that here. Let's go forward. Okay, so here's the dimethylation setup. You can see that you're basically going to save a parameter here in terms of your different experimental isotopic label setups. Let's set up a dimethylation experiment. So you're going to unlock one of these settings, give it a new name. Let's say we have two labels, a light and a heavy. That's going to be two possible mass shifts here. So let's call this native that has a mass shift of 0, and let's call this heavy dimethyl. And if I remember right, I may be wrong here, I think the mass shifts are like 26, I believe. So that's all you would do. If you had an additional heavy reagent, you would go in and add a third mass shift here. And you need to make sure that it has the same name here. And you can name these whatever you want. Let's say that's 32. Okay, and you just click Save, and that method's going to be there for you. Lastly, you just need to map your sample names to that experiment type, and you'll be good to go. Everything else looks the same. It's just like SILAC. All right, do we have any other questions?
Yeah, Eduardo asked any specific advice on when to upgrade to 2.6, and in relation to 2.3, should I do a BKP? I'm not sure what it would be. Oh, backup of databases. What do you need to back up when you're going from 2.3 to 2.6?
I always recommend doing a backup of your databases just in case. This is a direct install. It'll install right over. It should save all your databases and everything.
All right, so Eduardo, what that entails going to the program data folder, finding the ProteoIQ folder within program data, and just copy and paste the ProteoIQ folder somewhere else, and then just do the 2.3 uninstall and a 2.6 install, and you should be okay.
Yeah, you actually do not need to uninstall 2.3. 2.6 can install right over it. All right, listen, I'm here if anybody has any other questions about anything, even if it has nothing to do with 2.6, we're happy to answer it. So let us know. Otherwise, if we don't see any questions, I think what I'll do is we'll go ahead and just wrap it up. If anybody is installing 2.6, has any questions about the setup, please feel free to contact us.